Okay, let us continue the second part of today's course. Okay, in the first part, we have taught to page 127. By contrast, extensive experimental research that we have performed in Naparstek and Cohen 2018. Okay, let us see. Naparstek and Cohen, and the paper title is Deep Multi-User Reinforcement Learning for Distributed Dynamic Spectrum Access, which is published in IEEE Transactions on Wireless Communications in 2018. Demonstrated that the DQSA. Okay, what is DQSA? Let us review it. Okay, DQSA means Deep Q Learning for Spectrum Access. DQSA. Okay, let us continue to page 128. Okay. DQSA algorithm was able to deliver packets successfully almost 800 of the time, about twice the channel throughput obtained by the slotted Aloha, with optimal attempt probability. Okay, where does this value come from? Okay, we can see this paper, Naparstek and Cohen, in 2018. Okay, let us go to the reference. And I have downloaded this paper, Naparstek and Cohen 2028. Okay. And page down. Okay, in figure 3, channel throughput for the experiments conducted in section 5b. You can see that the x-axis is the time slot from 0 to 200, and the y-axis is the average channel utilization. Okay, you can see that the line for the slotted Aloha is about 0.37, and the DQSA can reach to 0.8. Okay, like this figure. Furthermore, note that computing the optimal attempt probability when implementing the slotted Aloha protocol requires knowing the number of users at each time slot. In contrast, the DQSA algorithm was implemented when each user learns only from its X signals, without online coordination, message exchanges between users, or carrier sensing. Next, we examined the rate allocation among users obtained under DQSA algorithm. We trained the DQN, Deep Q network, with different utility functions and demonstrated that users can learn policies that converge to good rate allocations depending on the desired objective. We first consider a network with 4 users and 2 channels, and trained the DQN to maximize the user sum rate. In figure 1.5, okay, let us see figure 1.5. Figure 1.5 is a representative channel selection observed about 80% of the time when maximizing the user sum rate. The x-axis is time slot from 0 to 51, and the y-axis are users 1, 2, 3, 4. Okay. There are three different colors in this figure. The blue color denotes no transmission, and the green color denotes channel 1, and the yellow color denotes channel 2. In figure 1.5, we show a representative example of the channel selection behavior among users. The presented policy after convergence was such that a single user transmits on each channel 100 of the time. Users 1, 4 in the figure. Okay, we can see that user 1, okay, transmit in channel 1 for 100% of the time, okay, after convergence. And user 4 transmit in channel 2 for 100% of the time after the convergence. While the other users choose not to transmit at all, users 2, 3 in the figure. Okay, we can see that users 2 and 3, they do not transmit, okay, after the convergence, okay, in this region. Okay, in terms of the user sum rate, such policies perform very well. Since each user contributes equally to the user sum rate, the users have learned a simple and efficient policy that achieves this goal. Furthermore, the channel throughput was greater than 0.9. Okay, you can see that, okay, for user 1 and user 4, okay, they use the total channel 1 and channel 2. Okay. We observe such rate allocations in about 80% of the Monte Carlo experiments. Although it achieves good performance in terms of user sum rate, the resulting policy in figure 1.5, okay, this is figure 1.5, performs poorly from a fairness perspective, because user 1 and user 4 always transmit, but user 2 and user 3 almost do not transmit anything for almost of the time. So it is unfair, or it is not fair for users 2 and 3. Therefore, we next examined the rate allocation among users when we trained the DQN such that each user aims at maximizing its own individual rate. That is competitive reward. In figure 1.6, okay, let us see figure 1.6. It is a representative channel selection observed about 80% of the time under individual utility maximization. The time slot is from 0 to 51, and there are 3 users, 1, 2, 3. And again, the blue color denotes no transmission, and the green color denotes channel 1. The yellow color denotes channel 2. In figure 1.6, we show a representative example of the channel selection behavior among users observed in about 80% of the Monte Carlo experiments. We consider a network with 3 users and 2 channels. Okay, you can see that there are users 1, 2, 3, and a channel 1 and a channel 2. Okay, in this case, we observe that a single user 3 in the figure, transmits on a single channel, channel 2 in the figure, 100% of the time. Okay, user 3 transmit in channel 2 almost 100% of the time. Okay, like this. While the 2 other users 1, 2 in the figure, equally share the second channel, channel 1 in the figure, using TDMA type scheduling. Okay, you can see user 1 and user 2. Okay, they almost transmit in channel 1, okay, in a TDMA type scheduling. Okay, this time slot, user 2 does not transmit, and user 1 transmit in channel 2. Channel 1. And in this time slot, user 1 transmit in channel 2, and user 2 transmit in channel 1. And in this time slot, user 1 transmit in channel 1, and user 2 transmit in channel 2. And from this time slot, user 2 transmit in channel 1, then user 1, then user 2, user 1, user 2, etc. Which one of the users receives a higher data rate depends on the initial conditions and the randomness of the algorithm. Finally, we examined the performance of the DQSA algorithm when we trained the network to maximize the user sum log rate, known as proportionally fair rates. In figure 1.7, okay, let us see figure 1.7. It is a representative channel selection observed in about 80% of the time under user sum log rate maximization. Okay, the x-axis is the time slot from 0 to 51. And in the y-axis, there are 4 users, 1, 2, 3, 4. And again, the blue color denotes no transmission, and the green color denotes channel 1, and the yellow color denotes channel 2. Okay, in figure 1.7, we show a representative example of the channel selection behavior among users observed in about 80% of the Monte Carlo experiments. We considered a network with 4 users and 2 channels. Okay, you can see that there are 4 users, 1, 2, 3, 4, and 2 channels, channel 1, channel 2. Okay. Note that the users effectively learn to equally share the channels, which is optimal in terms of proportionally fair rates. Okay, you can see that the blue region is the no transmission. And in this time slot, user 1 transmit in channel 1, and user 2 transmit in channel 2. And user 3 transmit in channel 1, and user 4 does not transmit. Okay, then for example, in these time slots, user 1 does not transmit, and user 2 does not transmit, and user 3 transmit in channel 2 and not transmit, and user 4 transmit in channel 2. Okay, and so on. User 1 no transmit, channel 1 2, no transmit, channel 1 2, no transmit, channel 1 2, no transmit. And user 2 similarly, no transmit, 1 2, no 1 2, no 1 2. User 3, no 2 1 2, no 1 2, no 1 2, no 1. And user 4, no 2, no 1 2, no 1 2, no 1 2, no. Okay, like this. It can be seen that the users effectively learn to transmit their data over channels during a batch of time slots and then stop transmitting data. Okay, batch of time slots. Okay, what is batch? In Chinese meaning, it means that 批次。Okay, 批就是一批两批的批。Okay, 批评的批。次呢就是次数的次。OK， 就是说一批这样子的 time slots 来进行传送。OK，for example, the user 1 do not transmit in this batch of time slots, and transmit in this batch of channel time slots in channel 1, and so on. As a result, they approximately equally share the number of time slots. Okay, you can see that they share the time slots in this manner. Okay, 1 2 no, 1 2 no, and 1 2 no, like this. Okay, finally let us see the conclusions. Okay, section 1.4. In this chapter, we presented an overview of DSA. Okay, what is DSA? Let us review it. Okay, DSA. Okay, DSA means the dynamic spectrum access. Okay, let us go to section 1.4. Okay, DSA algorithms for efficient spectrum sharing among users that coexist in the same frequency band. The operation of DSA algorithms is based on learning the environment dynamically based on partial observations. By continuously monitoring system performance and judiciously, okay, we have taught the meaning of this word to you. If you forget, please review our handout. Adjusting the transmission parameters to achieve high spectral efficiency. We started by focusing on online learning algorithms that were developed for learning the occupancy of the spectrum in the presence of external users to improve spectral usage. Then we focused on algorithms used to effectively allocate channels to users in a distributed manner. Okay, the Chinese meaning of the distributed manner is 分散式的, with the goal of maximizing a certain global objective. Finally, we focused on very recent developments of artificial intelligence, AI algorithms based on deep learning for DSA that can effectively self-adapt to complex real-world settings. Existing AI algorithms for DSA are based mainly on value learning, that is Q-learning methods to obtain the DSA policy. Okay, a future research direction in this respect is to develop policy-based learning and hybrid value policy learning that aim to learn the policy directly to improve convergence when the state space increases. Another research direction is to develop DRL. Okay, do you remember what is DRL? Okay, let us search for DRL. Okay, DRL means the deep reinforcement learning. Okay, deep reinforcement learning based algorithms when users transmit over interference channels with multi-packet reception. Okay, acknowledgements. This work was supported by the Cybersecurity Research Center at Ben Gurion University of the Negev and by the U.S.-Israel Binational Science Foundation, BSF under Grant 2017723. And the remaining is the bibliography. Okay, we have finished teaching chapter 1. Do you have any questions? Okay, if you do not have any questions, I prepared the homework 1 for you. Okay. Okay, this is the homework 1 of our course. Okay, the date of assignment is March 29th, 2022. And the deadline, I give you 7 days, April 5th, 2022. Problem. We have only one problem here. Consider the Markov chain xt where t is greater than or equal to 0 with state space capital S, which is equal to 0, 1, 2. Let the transition probability matrix be given by this. Okay, P is equal to 1/8, 3/8, 1 second, 1 second, 1/8, 3/8, 3/8, 1 second, 1/8. Write a computer program to determine whether the Markov chain is reducible. Okay, please hand in A, the source code of your computer program. 50 points. Okay, you can use any computer programming language. That is okay. For example, C, C++, MATLAB, Python, and so on. B, the output of your computer program, 50 points. Okay, notice. First, I encourage you to discuss with other students. However, if you copy someone else's homework solution, or you borrow your homework solution to someone else for him/her to copy, your score will be 0. Okay, second, if you hand in your homework after the deadline, your score will be 0. Third, please email your homework solution to Professor Wei Zhen Liu. His email address is comwcliu@ccu.edu.tw. Okay, I have make a hyperlink here. You can click on it. Okay, and your computer will open the default email software for you. Okay, it is 25 minutes. Let us take a break.